Okay, everyone. So we're going to be going through section 6.2 practice problems and just kind of quickly overviewing the concepts here. So this whole section is talking about the chemistry of a buffer. Okay, so the term buffer can kind of sometimes be a scary idea. It sounds like it's something that's really different or like kind of its own separate thing. But actually, you've been studying buffers all this time. A buffer is really an acid-base equilibrium that has to, so it has to be an equilibrium, which means it has to be a weak acid or a weak base. But really, the purpose of a buffer, or the purpose that we make this weak acid, weak base equilibrium, is so that we can try to maintain a certain pH level. Okay, so meaning if you were to add in some acid or base of a strong substance, an equilibrium will actually resist the change in pH because of the fact that we can do Le Chatelier's principle, right? So meaning that whatever stress you add to the equilibrium system, it will react and try to alleviate that stress. Okay, so a buffer is a solution that will resist a change in pH if you were to add in small amounts of acid or base that are strong. So the reason why we say only small amounts is because, of course, if you were to dump in, a lot of strong acid or a lot of strong base, basically it would just completely react with the weak acid or weak base, and then you'd eventually have just only your strong ions present. But anyways, so let's take a look at this. So here we have acetic acid, and we have our equilibrium. So let's say we started off with a 0.1 mole per liter of acetic acid. So we have 0.1 mole per liter. So we know that this will reach equilibrium, and eventually we can solve for the pH of the solution by determining our hydronium. And we saw this actually in chapter 5 when we did that. So when you are creating a buffer, okay, so what we're doing here is we want to speed up the process of our equilibrium being reached. So we know, of course, imagine like you're making this solution. If you give this time, eventually you'll have the rate of the forward being equal, the forward and the reverse, pardon me. So by adding in both the product and a reactant at once, what happens is you allow for the equilibrium to be reached much more quickly. So instead of adding only the reactant and waiting for the forward and reverse to be equal, we add in the same quantities or similar quantities. It doesn't have to be exactly the same, and we'll talk about that later, but similar quantities of in this case, we have our weak acid, and we have to add in its conjugate. So in this case, if we have acetic acid, the conjugate is the acetate anion. So, inside of a beaker, what I would do is we would add in our acetic acid, and we would add in a salt that has this anion in it. So, of course, we would want to make sure that it's a salt that's not interfering with anything. So usually we would pick, let's say, a salt that has a group 1 metal here. So potassium acetate or sodium acetate. We don't want that other ion to interact with anything else in this equilibrium. Okay, so the same thing could be said for a weak base equilibrium. So let's just write this in quickly here. Okay, so here, if I wanted to create this as a buffer solution and I wanted it to have equivalent amounts of base and the conjugate, let's say I put in 0.10 mole per liter of ammonia, I would have to add in a similar quantity of its conjugate. So in this case, I would need to add in a salt that has the ammonium anion. Now, the, cation. So what I would put this with is with an anion that will not interfere with this reaction. So for example, I can do ammonium chloride. So if we saw in 6.1 that certain negative ions could hydrolyze with water, so you want to pick something that is the conjugate base of a strong acid. So chlorine ions or bromine or iodine would all work here. So if we were to add in both of these components, we would have our equilibrium be reached, and we would now have what we call a buffer solution. So buffer solution normally exists with a weak acid and its conjugate weak base in approximate equal concentrations, or if you're dealing with a weak base, it would be with its conjugate weak acid. So the way that we set up the equilibrium here is the same that we did when we learned about pKa and Ka values. It's our products over the reactants, and remember we don't include our water. So this is the same acid buffer that we had in the slide before this. So if we wanted to solve for hydronium to solve for pH, we would essentially have to know all of these other pieces of information at equilibrium. But remember, if we know what these concentrations are of our acid and our conjugate base, we would be able to have that information because we're going to be at equilibrium. And we'll get through some practice problems, but just to kind of show you where that formula is coming from. So the simple but important equation means that the hydronium ion concentration of a buffer depends on two factors, of course. So it's going to depend on the Ka value of the conjugate of the weak acid that you're using, and it depends on the concentrations of the two items that you're adding into the solution. So let's say, for example, that we had the same concentration like we had in that other example. That means that the ratio between HA and A would be approximately 1, okay, if they were in equal concentrations. Now we'll talk about what happens if they're not exactly equal, but you want to try to get them as equal as possible because you'll notice in the next couple of slides that the range of that ratio will depend on, or basically affect how efficient your buffer can be. All right, so let's start taking a look at what happens to the pH once we have a strong acid or strong base added to our buffer solution. So when we have our buffer, so originally it was written like this, just to kind of remind you. Okay, so let's talk about what happens when we add a strong acid to this buffer. Essentially what's happening here is all of the hydronium that is added from that strong acid. So remember that if you have a strong acid, really all of those ions are being produced. So essentially if we have like HCl, all of the hydrogens in that HCl become hydronium. So when you add in hydronium, it's going to essentially push the reverse reaction of your buffer to occur. So I know this is written as if it's a forward reaction, but if you look at your original equilibrium, it's actually the reverse reaction, right? So if I have an increase in hydroxide, what happens is the I said hydroxide, I mean hydronium, I'm really sorry. So if I increase the hydronium ion concentration, it's going to react with our acetate anion to produce our acetic acid and water again. And I just realized I missed out on my CH3 portion here. So all of the hydronium that's been added will be converted back into acetic acid and water. So the concentration of your acetate will lower and the concentration of your acetic acid will go higher. Okay, so let's do this again. So I'm just going to do it with kind of simplified equilibriums here. Okay, think of it as Le Chatier. If you increase the amount of hydronium, it's going to push the reverse reaction to go to the to be happening faster, right? The reverse reaction is favored. So in order for the reverse reaction to happen, the anion here will have to be consumed because it's going to be reacting with the hydronium to produce more water, which we don't care about the concentration of because it's a liquid. We'll care about the concentration of our weak acid. So the weak acid goes up and the conjugate base will go down. Now, the reverse will happen if we were to add in a strong base. So if we were to add in a strong base into a buffer equilibrium, remember that the strong base will fully dissociate and we have hydroxide ions. So when hydroxide is with hydronium, it's going to essentially cause a side reaction. Like the hydronium and the hydroxide are going to neutralize each other. So what happens is the Le Chatier principle indicates that this is going to shift to the forward reaction because it's going to try and replenish that hydronium that's been lost. So as a result, we're going to have an increase in our conjugate base concentration because we're making more product, and our weak acid concentration is going to lower. But the point is that even though you're adding strong acid or a strong base, you will eventually reach equilibrium because remember, we're only talking about adding this in small amounts. Okay, so like I mentioned, if we were to dump in a bunch of NaOH, we could react all of the hydronium, push this forward, continue reacting with it until essentially we have no more that is remaining, like you would fully neutralize it. But that's not really the purpose of a buffer. The buffer is to maintain the pH or the equilibrium as long as if you're dealing with small quantities. So over here, this is showing you an example. So here we have our original concentrations of our buffer. So notice we have the acid and our conjugate base in equal quantities. So that ratio we were talking about on the slide before is a ratio of 1. After we add in some strong acid, what happens is some of it is going to essentially push the reverse reaction. So which we just mentioned here. So that means that the weak base should lower and the weak acid should increase. So this increased and this decreased. So what happens as a result is the ratio is now no longer 1. We now have, and it's always product over reactant for our K value, but remember that we're rearranging that to solve for our hydronium. So the ratio is your acid over the conjugate. So if you were to calculate the hydronium here using the ratios that are given, so the initial one is essentially the Ka value times the ratio. So in this case, it's the Ka value for acetic acid times 1. So this is our hydronium concentration, which gives us a pH of 4.74. After adding in that small amount of acid, we're now multiplying it by our new ratio. So that's going to change our concentration. So it should make sense that it is a bit bigger because we have more hydronium that was added in. And our pH went down a little bit, which again makes sense because we added in a small amount of strong acid. It should go a little bit lower. But the point is, because this was in equilibrium, it did not lower significantly. Like if we did not have a solution in equilibrium and we added in a strong acid, it could go down to like a pH of 1.5 or 2.1. So even though it did go down because you're adding in a strong acid, it's not a super significant change up. Okay, so let's take a look at adding a strong base in our next part.